Okay, good morning. Thank you very much for rejoining. This has been a great school so far. And I'm sorry I had to give this talk a little later in sequence, even though you've had talks on galaxies already. And this was originally designed to introduce you to galaxies. But that's why there will be some repetition in here. But I'm going to talk about various things that have been not been covered so far. You've heard about galaxies. You have heard about radio galaxies in AGN. You've heard about our own galaxy a little, and you've heard about clusters of galaxies. But let me just talk about why this is a new subject to begin with. And this you must have already encountered before. But the thing is that even at the beginning of the 20th century, even when, for example, Einstein was publishing his theory of relativity, it was not known that we live in a galaxy. And I wanted to introduce that to you first, uh, in a brief manner, just to show you what the main difficulties are in studying galaxies and also figuring out the large scale structure of the universe. In that, even 100 years ago, we did not know the scale of the universe, the age of the universe, as well as the fact that we live in galaxies. So this is because if you look at the sky, if in general you see stars through a naked eye or a small telescope, but when you look through a big telescope, you look beyond these stars that are apparent to the naked eye, and you look at galaxies, right? And these are galaxies, and this is what people struggled for a long time, starting from Herschel's time when he had built big enough telescopes to look at and distinguish between things that are small and point-like and twinkling in the sky, and things that are much larger and nebulous, as various people noted, and they are fuzzy objects. And so, for example, in this particular section of the Hubble Deep Field, we see only two stars, which are like stars here, but much fainter. But the everything else we see are galaxies, and you already know what galaxies are. But I wanted you to appreciate that this is not an easy thing to figure out. And this is why we we waited till such a long time. And I'll take you through a couple of these points now. And this is because when you look at these fuzzy objects in the sky, that was identified first by Herschel in the 1780s, and Messier in France. Around the same time, they made lists of fuzzy objects in the sky, things that are not point-like, they don't twinkle, and through a small telescope, they look like they're extended. And they were trying to figure out whether they're stars or there's some atmospheric phenomena, they're comets and things like that. So you can see that I've put four objects here, which are very different objects, but they were all identified as exactly the same kind of thing, which is non-point-like. And they are all part of, say, the Messier catalog. So they'll have M1, M3, M27, and 51. Herschel had his own catalog of such things called the NGC catalog, which we now call the NGC catalog. And now, with modern telescopes and modern observations, you can see that these are very different objects. And that is because we've learned how to measure distances to these things, which they did not. So the first thing is that the lack of a good way of measuring distances was the main problem we had in figuring out how far away these things are and how big these things are. And so, for example, here is the Crab Nebula, which is M1, which is just a single star that has exploded that looks nebulous. Here is a planetary nebula, which is essentially a star, again a single star, but it's now gone beyond its main sequence, and it's losing mass. And these are at similar distances, kiloparsecs, and they are exactly the same size on the sky, 8 minutes, 6 minutes. And then you have this is a globular cluster, M3, which was classified same thing, but it has 1,000,000 stars in it. And that's because it's same size on the sky, but it's much further away, about 10 times further away. And then you have a whole galaxy here. And there are many galaxies in the NGC and Messier catalog. And this is megaparsecs away. And but it's the same size on the sky. So these things look the same. You know, the sun and the moon are the same size on the sky, but they're very different objects. But you needed to know how far away the sun and the moon are to figure out how different they are. And so this is why there was this big debate that went on. And now we know that there are all these different kinds of galaxies, and you have heard about this quite a lot in the last 2 or 3 days, if not before. And we know that there are elliptical galaxies and spiral galaxies, different kinds. And we also know that galaxies interact with each other and merge with each other. Yeah, and we'll see a little bit of. So when it was sorted out, and I'll tell you in a minute how it was sorted out, that these things are actually galaxies, they're building blocks of the universe. And they are the molecules of the universe, as it were, so that the units in which all the various interactions between stars and gas, etc., take place within the galaxy, but they are independent. They also interact with each other, but most of the physical evolution takes place within the galaxy. And Edwin Hubble, who figured this out in the 1930s, classified the galaxies along to this so-called tuning fork diagram, which you have come across before. And this he kind of thought, because the elliptical galaxies, which look very simple and round or ellipsoidal, they are uncomplicated. And so he thought that's how galaxies form. And then they evolve structure and become more complicated. And so he had this interesting diagram in which he thought elliptical galaxies form first and then they become spiral. And there are two kinds. He found that some of these spiral galaxies have bars in them like this. And so those are a different kind of object. And so they are very different. We now know that this diagram is completely wrong, even though this forms the basis of a lot of textbooks. They're wrong in many, many ways. And this is, for example, I started with this diagram, and it's taken from the Spitzer catalog of nearby galaxies, in which if this is an evolutionary sequence, it shows the diversity of the galaxies, and it really shows that there is not a single kind of way galaxies evolve. If anything, this is wrong in two ways. One is there is no difference between barred spirals and normal spirals. We now know that spiral galaxies develop bars and spiral arms, and they're transient phenomena in their life. Bars come and go. So the same galaxy can be a barred galaxy today, and a few 100 million years later, it is not a barred galaxy, a very transient phenomena. Similarly, the spiral structure itself can be a transient, and the number of spirals it has can come and go. The other thing is that we now know that galaxy evolution doesn't progress this way from ellipticals to spirals, but goes the other way around. We now know that the young galaxies that are formed are flat galaxies like this. They're flat because the initial cloud that collapses to form galaxies actually preferentially collapse in one direction. And so because the cloud has an angular momentum, and as the collapse happens, the spin goes faster to conserve angular momentum, and angular momentum always determines a certain axis. And so it also gives a preferred axis for collapse. And often the cloud will collapse perpendicular to the axis of rotation. And so the disk that results out of that collapsed object will continue to rotate and maybe rotate at a much higher speed as the thing collapses, right? So we have spiral galaxies that rotate. Now, it is very difficult to get rid of the angular momentum. And we see on the right-hand side how galaxies actually collide and merge with each other. And once galaxies with different angular momentum vectors, which are pointing in different ways, actually merge, they destroy each other's angular momentum. So the only way to reduce angular momentum in free space where there's no friction is to actually merge with something that has an opposing angular momentum. That's the best efficient way to do it. And we now know as galaxies merge, they lose their angular momentum and as a result puff up. And so these elliptical galaxies, ellipsoidal galaxies, have very little angular momentum. They're not rotating as much, and they are supported by the velocity dispersion of stars, which are the random motion of thermal motion of stars within them. So that is the way. And we also see that elliptical galaxies have stars that are very old, preferentially much older than in spiral galaxies. And in spiral galaxies, we see ongoing star formation more frequently. It is very rare to find ongoing star formation in elliptical galaxies. Elliptical galaxies has much bigger and much more evolved black holes in them and things like that. All these point towards the fact that actually Hubble got the direction of evolution wrong. We still have this portrait to you, but I wanted you to know that that actual evolution is very, very complicated, and the variation amongst galaxies is much bigger than Hubble thought, and bars are not the way to distinguish between galaxies. Right. So, having said that, we know that galaxies operate on a very different distance scale altogether. You've had lectures on various things. You've had lectures on stars. You know the average distance between stars about a parsec, light years, parsec. The size of a normal galaxy, 30, 50, 60 kiloparsecs. That is the size in which our radius of our galaxy is about 30 kiloparsecs. And this is the stellar part of the galaxy. As you know, galaxies have dark halos and dark matter halos, which can be much, much larger, many hundreds of kiloparsecs. In fact, our neighboring galaxy is 700 kiloparsecs away, and we don't know whether the Andromeda galaxy or our galaxy, where our dark halo really ends, whether they are touching or whether they are just a couple of hundred kiloparsecs. So the actual size of the galaxy is not well determined right now. We see the stellar part of the galaxies, which also has the gas and the dust. And the average distance between galaxies is about a megaparsec. Our nearest galaxy is 0.7 megaparsecs away. Quickly talking about the debate, that it actually shows a very interesting thing of debate that led to our identifying galaxies as the unit of the universe. 1920, we celebrated last year the centenary of the Shapley-Curtis debate at the National Academy of Sciences in Washington, where the debate happened between the two of the most prominent observational astrophysicists of the US about what these fuzzy objects were, right? And I showed you this picture and showed you modern pictures and with distances measured to them to show you what they were. But 100 years ago, it wasn't known to these two gentlemen. And Shapley, who will later become probably the most important observational astrophysicist on galaxies of the century, actually was on the wrong side of this debate. He actually is the person who 5 years later will call these things galaxies, give the name galaxy. But he thought at that time that these things were stars. All of these fuzzy things were actual stars. And the whole universe was what we now call a galaxy, which is about 100 kiloparsecs across. In that debate, he argued that these stars and these fuzzy stars, the nebulae, fill the whole of the universe. And the universe itself is very small. 100 years ago. And Heber Curtis, on the other hand, said that our galaxy is about 10 kiloparsecs, and all these other nebulae that you see are actually like our own galaxy, and they are maybe 10 kiloparsecs across. They're spread all over the universe, and the universe is much, much, much larger. Okay. And the reason this happened, and this is an example which I would like to cite here, because it shows how data, if you actually take data and don't consider the source of the data or the possible errors in the data, how it can be misleading to you. And these are very sophisticated scientists working as contemporaries of Einstein at the same time in observational astronomy. They are the top people. And they believe certain data that were not right. First of all, there was no notion of how much dust there was in the intervening space between stars. But what Shapley did was Shapley really trusted the work of one of his colleagues called Van Manen, who was a very important at the University of California, a very important observational astronomer. And what he did was he took some pictures of galaxies, they didn't know galaxies then, these nebulae, say M81, this is another of the nearby, we now know galaxies about 5 megaparsecs away, but he did not know that. What he did was he took that and he looked at pictures taken years apart over many, many years. and he put them together and said that within a few years, he could see that the stars had moved, and so this galaxy was rotating. So he measured rotational speed of the galaxy from comparing nearby photographs. And he did this for 4 such nebulae, and found that these rotational period in years were something like 45,000, 50,000 years. The whole thing rotates, right? And then he determined an upper limit to the distance. And he said that if it's, for example, more than a few kiloparsecs away, these things, then these speeds would translate into linear speeds that will exceed the speed of light. Okay. Now it turns out that, so you can see that if you just take distance to M101, and you could see that the velocity would very much exceed the speed of light if it is at its distance that we know now, which is 5 megaparsecs. Okay. So it turns out that the rotational period now we know is actually 2 times 10 to the 8 years, but he measured it as 85,000 years. And this is why Shapley thought that these things were much closer and the universe was much. Later on, it was found that his calibration was totally wrong in terms of registering the different pictures, and the pictures that had been taken about 30, 40 years apart, there's no way you could have measured any shift of the stars. So this is a good example of what misled the people. And now we know that galaxies are megaparsecs away. The nearest galaxies are megaparsecs away. And of course, the most distant galaxies that we've measured are much more than that. That's thousands of megaparsecs away. So we come back to our galaxy, and then I would like you to read about the Shapley-Curtis debate. This is a slide that I took from Frank Shu's book called The Physical Universe. It actually has a very nice exposition of it, but on the web there are many resources. Go and look at it, because it's a good example to show how even the top people in the field can make a very, very important mistake if they take certain data seriously. And this is very true in astronomy, because in astronomy, we cannot really go and touch our objects. It's not like a normal lab in which you can change an experiment or actually look at the experiment and do it in different ways. The experiment that is the universe is given to us, and we have to make observations, clever observations from here on Earth. And based on the data that we get, we have to infer what the reality is. Okay, so based on a lot of observations, we now know that this is our galaxy. These are not pictures, of course. You can't take pictures of our own galaxy. You heard about our galaxy yesterday. And so we know it's very flat and it's rotating. And we are not at the center. We are about 8 kiloparsecs away, 25,000 light years from the center. And there's the massive black hole, supermassive black hole right in the middle here. And there are these 5 arms, and then the sun is close to one of these arms currently. And from inside, it looks like this. This is a picture taken from Chile, where when you're looking at stars, you're looking through a screen like this on different sides, but you're looking towards the center of the Milky Way, towards the bulge. You can see it as what we call the Milky Way, which is a band of stars across the sky, and you can see this dust which is in the plane of the galaxy, and that dust shows up, and from the southern hemisphere you can see it much clearly, and this dust, and here is the center of our galaxy, Sagittarius, right in the middle. In the same plot you see 2 other things which you don't see from the northern hemisphere, and these are called the Magellanic Clouds. They're called clouds because they look like clouds. It's really a fantastic sight when you go to the southern hemisphere. They look like clouds. They're hanging in the sky. They don't go away. And these are our nearest major satellite galaxies. The Milky Way has many satellite galaxies, and these are naked eye objects from the southern hemisphere. And of course, from the southern hemisphere, if you are in clear sight, our own galaxy provides enough light for you to read a book on a moonless night. And you can see that now these are real pictures. And this is what our galaxy would look like if you are outside our galaxy. Very similar. They're relatives of the Milky Way in the sense that they're lookalikes. Our galaxy would look like this. And you can see that if you turn it in angle, you'll start looking at exactly what we saw in that picture from Chile, right? And this is, for example, one of these pictures, the real pictures of the Milky Way, an all sky picture taken with a fisheye lens, and you can see how similar these are. So this is, and 75% of all galaxies are spirals. They have different levels of spiral arms and things like that. Now, galaxies, these galaxies have these spiral arms, and that is because they are aligned with ONV stars, which are newborn stars, which actually form in molecular clouds. And these molecular clouds actually happen to lie along these spiral arms. And in fact, the perturbation that causes the spiral arms often causes molecular clouds to collapse and form stars. And so there's no surprise that they line the spiral arms, and so they are seen as very prominent. Now, actually, even though the spiral arms turn out to be very prominent in the galaxy, the actual overdensity represented by the spiral arms is not that prominent, and they are very prominent because they have the brightest stars in them, and you have associated with star formation. Most of the star formation is happening along these spiral arms, and associated with the star formation is the dust and the gas that go with often go with star formation. And you must have heard about how some of this dust can glow in the infrared. And so if you take an infrared picture of this, you will see the dust that goes in the along with the star formation. And then you can have the gas, the cold gas, which is seen in radio observations. But stars are mostly uniformly distributed in the disk with these minor perturbations that form the stars, the spiral arms. Now, actually, the spiral arms don't represent the rotation of the whole galaxy, because this is the so-called the winding paradox, which you might read about. That tells you that if, for example, the spiral arms are the result of the rotation of the whole galaxy, then the spiral structure would actually, if the way the galaxy is rotating, the spiral structure will be wound up so much that you won't see them as spirals as you see now. You would see like a spring, a circular spring like that. And they are not completely related. And the reason you see the spiral arms are like this very interesting analogy is that if you, for example, see cars going around on a highway, and there are certain places on the highway where they have to slow down because there's a traffic light or something like that, and then there are other places in between traffic lights where the cars go much faster, and then they slow down, and then they go much faster. And if you take a snapshot of that, you will find that on the highway there are places where there are concentrations of cars, and other places that there aren't because they're very sparse and things like that. And so so this is called a density wave, and the density wave is exactly what you're seeing. So there are certain perturbations in the disk of the galaxy in which, as stars go around and round and round and round the galaxy, they slow down and feel that perturbation, and they slow down around them and they crowd around that perturbation. So it looks like that there is a spiral arm, and then they move faster in between the spiral arms. And so when you see a spiral arm feature, or it actually applies to a bar feature as well, when you see such a feature, it is not the same stars. Just like in a traffic jam or a traffic slowing down on a highway, it's not the same cars that are there. If you take snapshots every hour of a highway all through the day, you will see near the traffic lights or near the crossings that there will be a larger density of cars, but they will not be the same cars all day, right? Because the cars would have gone and new cars would have come. The actual congestion is happening because of the conditions, the local conditions there. Similarly, if you look at the spiral arms, you don't see the same stars. And as I showed you right now, our star, the sun, is near the Orion arm, and it's going to go between the arms much faster and the star pattern is going to rotate much slower, right? And so then along these patterns, you have these regions of star formation, which are the molecular clouds, etc., that are forming stars. And right now in our own galaxy, we have all these arms, and there's the sun in the Orion arm. And it's interesting that people have done this exercise of figuring out that in the many times that the sun has gone around our galaxy, what kind of effect that has had on the sun and the earth, because they must have passed through these overdensities and underdensities many times. How many times has the sun gone through our galaxy? I don't know whether anybody did this calculation before, but let me quickly look at this very quickly. If you haven't done this calculation before, and it kind of shows how stars go in a galaxy. So it's rotating in this way, our galaxy, and I said that it's near the Orion arm now. Now, the galaxy is rotating this way, and the sun is rotating this way. And if you look at the sun is now traveling within the disk of our galaxy at about 220 kilometers per second in a mostly circular orbit around the center of our galaxy. And the distance away from the center is 8 kiloparsecs, and 8 kiloparsec, 1 parsec is so much. If you do a very simple calculation, the time taken for the sun to go around the galaxy is 2 pi r over v. You put this velocity, you can turn it into, it's in kilometers per second. R is 8 kiloparsecs. You can turn that into kilometers. You can take the fact that a year is about 3 times 10 to the 7 seconds. And the simple formula tells you that the time taken by the sun to go around the galaxy is about 250 million years, right? 0.23 times a billion years. And you know that the Earth and the sun are 4.5 billion years old, right? So if it takes 250 million years, then it just shows that the sun has gone around the center of the galaxy about 20 times, right? So the sun is moving much faster than the galaxy is turning, and it's gone around 20 times. So that must have had a very interesting effect on the Earth and the sun as they went around the entire neighborhood, entire galaxy many times, right? And so it's very interesting to figure out what that, from the Earth's history, what effect going around. And of course, there is also a motion, a Z motion. So it's going around in 20 times in the age of the Earth or sun, but it also has a motion perpendicular to the disk as well, with a different periodicity. Now, what is happening near us? And here is a picture of, say, the local group. Our sun, our galaxy lives in a small group. You heard about clusters of galaxies yesterday, but most galaxies live in small clusters. They often 2 or 3 big galaxies, along with lots of tiny galaxies. But here you are. Here we have our galaxy, which is the Milky Way, along with Andromeda, which is our nearest galaxy, at 0.7 megaparsecs away, which is similar to us, but maybe about a couple of times larger than us, Andromeda. But these have their own satellites, like Saturn has 60 moons that we know of. We know of about 42 satellites of our own galaxy. We know about 45 satellites of Andromeda right now. And the number is growing. Every year we find another satellite galaxy, the very tiny ones. And just like the moons of the planets, these galaxies are much smaller than our galaxy. And sometimes we are actually finding galaxies that are stretched all around the sky, because these galaxies are being torn apart by the tidal field of our galaxy, and they're falling into our galaxy. So we know that small galaxies fall into the large galaxies all the time, and this is happening in our galaxy right now. But here the Sagittarius dwarf, for example, is a galaxy that is seen actually 270 degrees across the sky, and maybe it's even 360 degrees. And because it's stretched, all its stars are stretched under gas. and it's because it's going around, it's breaking up and slowly sinking into our galaxy. Other than that, this picture shows only a few of these dwarf galaxies, which are at least 1,000, if not 1,000,000 times smaller than our galaxy. Some of these are much, much smaller. They're our galaxy, if it's 10 to the 12 times the mass of the sun. Some of these galaxies are 10 to the 7, 10 to the 8 times the mass of the sun. So they are very, very tiny. And so they all major galaxies, they're minor galaxies around them. And then these two are actually coming towards each other and will merge together into a galaxy in about 4 billion years or something like that. Right, so the groups often are collapsing groups in which the galaxies, the Magellanic Clouds. Just look at, I'm going to show you some pictures of these dwarf galaxies and how different they look from the giant galaxies, which are nice and round elliptical, or disk galaxies that have the spiral structure in them. So I'm just going to show you some pictures of these dwarf galaxies. If you remember, the large Magellanic Cloud and the small Magellanic Cloud were in the picture I showed you from Chile, where we showed the Milky Way and the two clouds. So here they are. These are the two galaxies, and you can see them in this picture. This is an infrared picture of the sky in which we are looking towards the center of our galaxy, but we also see the two Magellanic Clouds. And this is the large Magellanic Cloud zoomed in, and you see what a mess it is. It is not a very regular galaxy like the elliptical or the spiral galaxy. And 30 Doradus is a cluster within LMC, which is so bright in terms of the formation of stars that if it were in our own galaxy, we'd have seen it during the day. It's very, very bright. And then it's much larger than the moon. The moon is 0.5 degree on the sky. The large Magellanic Cloud is almost 5 degrees on the sky if you take all the different parts. And then this is the SMC. You can look at some of the other dwarfs. And some of them you can see very nicely in these pictures, and some of them it's very hard to see where the galaxy is. A very small overdensity of stars, very, very faint. And these are, and that's the 0.5 degree the size of the full moon. And you can see how big these things are, but they're very, very faint. And this because they're very tiny galaxies. And so finding this is a very interesting way of doing it. And so people are doing this, for example, in surveys, all sky surveys like the Sloan survey or whatever. Mike Irwin at the University of Cambridge started doing this kind of thing with photographic plates in the early 90s, and now it's done with digital photographs, where what you do is you look at a picture of the sky in one part, and then you do all kinds of image processing on it to smooth something and subtract from it and look for differences and to find things that will come out. And so things like, I mean, he was the person who discovered Phonax, for example, and to find Phonax, these faint galaxies, it takes a lot of massaging of the data to do this. The SDSS, for example, in the entire survey, developed 20 satellites of our own galaxy. This is a galaxy catalog survey in which to find faraway galaxies, but it also takes pictures of about 1/3 of the sky, and from the stars found in the sky, these satellites were discovered. And as I said, the Sagittarius dwarf galaxy is like this. It's, as I said, 270 degrees discovered all across the sky. And this is a star map. It looks similar if you find it's cold gas and stuff like that. And you can see how it is like in a whole part of a stream. It's an arc across. So it's not galaxy is being torn apart. It's only 25 kiloparsecs away from the Earth, the nearest part now, from the galaxy nearest part now. And the tidal field of our galaxy is essentially stripping it apart. This happens all the time, so it is absolutely certain that many of the other satellites of the Milky Way have fallen into the Milky Way already. And we now know that LMC and SMC, the Magellanic Clouds, are actually also part of a stream called the Magellanic Stream. You can see it clearly in radio observations, a stream of cold gas actually surrounding. You can see this in other clusters. This is a cluster, the Virgo cluster, and you look at them and you can see this happening between galaxies in the entire cluster. Deep images in the optical show, and if you combine it with radio observations of the gas, it shows that how galaxies, when galaxies interact, they tear each other's stars and gas out. And so the smaller galaxies are more vulnerable. They are easily disrupted or destroyed, and they go into the bigger galaxies. So the message to take away from this is galaxies are evolving. They are not really the island universes that Shapley and Curtis then finally thought. They are also interacting with each other. And so they're constantly changing, but they form these units. If you look at Andromeda, which is our nearest galaxy, and then you take a very deep image of this is a Keck telescope image of it, you can see how they discovered all these little satellites of Andromeda from these deep Keck images. This is a mosaic, and you can see the stream of stars joining these two. This is flipped now, so that's M32, M31, and NGC 205, and you can see there are lots of stars being exchanged between them. There are all these intergalactic stars and these streams, and all these little and 3 and 4, whatever, all these little things are dwarf satellites that are independent little galaxies around them. So there's a lot to be done here in terms of trying to identify the small galaxies, and their lives of these small galaxies are very different from the big galaxies. And when galaxies emerge, they don't involve, stars themselves don't emerge. They often, the gas collides as the stars collide, and they can lead to star formation, new stars being formed. And for example, if you look at the small group of M81, this is one of our nearby galaxies, and you can see its two neighbors, M82 and NGC 3077. But from the optical picture, you won't see much. You'll think that they are very nice and quiet and a boring picture. If you look at the radio observation of these galaxies, and this is on the left-hand side, is the H1, the 21 centimeter observation of the cold gas from the galaxies. You can see how much the three galaxies are interacting with each other in terms of exchanging gas and the tidal interaction that's happening between them. In fact, this tiny galaxy, M82, has one of the highest rate of star formation that we know in the nearby universe. It's called a starburst galaxy, and it's forming much more stars than the other two. This is a giant galaxy, this is a dwarf galaxy, but this has more stars being formed per year than this entire galaxy together. And so this is thought to be because of the tidal influence of the giants and this interaction that's going on. Now, you wouldn't know about this interaction unless you actually looked at the radio image. This is why radio images of galaxies, and this is in the emission line of atomic hydrogen, which is the 21 centimeter line. And so this kind of reveals a lot of the interaction that's going on. Similarly, you know another very famous interacting galaxy, and you can see whether, I don't know whether this will work, is a reconstruction of how such a interacting galaxy image can be formed. And you can see a giant galaxy and a not so giant galaxy interacting together and forming the debris. And these are actual simulations taken with all the dark matter and gas and dust all put together, and you can see how these interact together as they go around, and various features form in them. This is trying to reconstruct the actual current morphology of the interacting galaxy called the mice, and you can see how it falls in again, the center part, and it's going to get and goes past. And the final result looks very much like what we see on the sky, right? So this is another very interesting way of looking at simulations that would do this. And similar thing will happen to our galaxy and the Andromeda galaxy as it comes towards us. The galaxies evolve by merging. This is an example of a major merger, which means two major galaxies merging, and minor mergers happen all the time, right? As galaxies fall through. So I'll go past this. I won't talk about that. You also know that in the middle of our galaxy is the supermassive black hole, and The supermassive black hole, other people have talked about it. I just wanted to mention it just for completeness that we talked about the fact that galaxies have cold gas in them. Galaxies actually have hot gas in them, which I'm going to talk about. Spiral galaxies have a lot of cold gas in the disk, which you saw in the interacting galaxies, how they're exchanged and things like that. But the supermassive black hole in the middle of the galaxy, you heard about when Professor Saike talked about AGN and its effect. You also know that this year, the characterization of the supermassive black hole in the center of our galaxy was awarded half the Nobel Prize by looking at the orbits of these star cluster near Sagittarius A star, which is where the black hole is, and all those, and these two people got the Nobel Prize this year by looking at the motion of the stars around the central black hole, and by using Kepler's third law, essentially the relativistic version, found that the supermassive black hole in the middle of our galaxy is 4.4 times 10 to the 6 times the mass of the sun. Now, it turns out that when you look at the spiral galaxies, you look at the bulge, which is smaller than in elliptical galaxies. Elliptical galaxies is mostly bulge, no disk, and the mass of the black hole correlates with the mass of the bulge. So in elliptical galaxies, the supermassive black hole is much, much more massive. And so you get things like 10 to the 8, 10 to the 9 times the mass of the sun in the black holes right in the middle. And that plays a very important role in the life of the galaxy and the evolution of the galaxy as it can turn active, which you heard about before. Now, the last thing I'm going to talk about is in the evolution of galaxies, in the life of galaxies. Star formation plays a very important role because it shows whether the galaxy is essentially alive in terms of forming new stars, and thus widespread change around the galaxy is possible. Now, if you look at this this is an old plot, but it actually shows the basic features of the star. If you look at this is the y-axis, gives you some idea of the star formation rate density. It just shows you the amount of stars being formed in galaxies per unit volume. And the x-axis shows the redshift. Redshift meaning the distance away from us. Further away you go, the redshift is higher, but you also points out to an earlier epoch of the universe. So a z of 5, a z of 3 means the time when the universe was 1/4 of its age. So you're looking at much earlier times, and so you can see that the star formation rate actually increases quite a bit, and it peaks at about in between the redshifts of 1 and 2. About 2 it peaks, and then it falls very sharply to the current epoch. So it means that currently the average star formation rate in galaxies is very, very small compared to when the universe was twice or thrice younger. And this means that at some time, even galaxies like our galaxy was forming a lot of stars. Our galaxy now forms about 1 solar mass per year at a rate, which is a very tiny rate. It's not, even though it's a spiral galaxy, it's better in that number than the average elliptical galaxy, but there's not much star formation happening, right? So there's a big debate about whether this is nature versus nurture. I mean, essentially, whether the star formation, the fact that star formation rate fell down in the last half of the age of the universe is due to the fact that galaxies on their own kind of used up all the fuel for star formation. So gas consumption, it's an internal matter, normal aging, or it was external in that external effects, the environment made sure that the star formation went down. So we want to look at the difference between these two scenarios, and this is still a matter of debate, but very interesting things are emerging. We also see that galaxy clusters, which you heard about quite a lot yesterday, are places where it's full of galaxies that don't form much stars. They're red and dead galaxies, mostly elliptical galaxies. Elliptical galaxies are very old stars and dead galaxies, in the sense that there are very little ongoing star formation. So this kind of tells you that maybe the environment of the galaxy is very important in this kind of evolution, in the quenching of star formation, right? So the idea is that we know that elliptical galaxies only are predominantly found in clusters or protoclusters, and then they have these galaxies. There's also a very important relation called the morphology density relation, and somehow my color scheme of this slide is not working very well. But this is from Dressler, 1970, very old. And the interesting thing is we rarely show plots from 1960s, 1970s, because astronomy moves so fast that that they become very largely outdated. But there are certain plots from the 1970s or 1960s that are still shown in talks like this, because they are very important. The effect still is there. And what Dressler did is very interesting. He looked at photographs of galaxies and then counted the number of galaxies around each galaxy, and then noted what the galaxy's morphology was: ellipticals, spirals, or S-naughts. What you can't read in yellow is that these dots are spirals, the circular dots are spirals, and these are ellipticals. And then he plotted on the x-axis the density of galaxies around each galaxy. So he takes a kind of an area and says so many galaxies per unit area. Okay, and on the right hand side, on the y-axis, is the fraction of the population in that region. So you can see that he finds that the elliptical galaxies rise with increasing local density. And this is the picture that I showed you here. That is the highest density of galaxies in the centers of clusters. Centers of clusters, the maximum you can get is half the galaxies are elliptical, right? But normally in very low density regions, 10% or less galaxies are elliptical. And then correspondingly, you can find that spirals will drop down, and in clusters of galaxies, the number of spirals is very little, and in the field they are the maximum. They are the maximum, and in between are the S-naughts, which are the lenticular galaxies, which are the in-between type galaxies, and they fill in the base. So from this, he essentially tried to argue, and still a lot of people argue, that it is the local environment that is responsible for the quenching of star formation and turning spirals, the spiral-like star formation, into the elliptical-like conditions, and also turning this global redshift-dependent star formation of galaxies into the dead galaxies now, as you see here. The fact, so this effect is mostly, so what are these physical processes that can transform galaxies? This is my last point, really. What in these high density regions can transform galaxies? And what you can see is that, for example, if a galaxy moves through a high density cluster in which there's a lot of gas in between the galaxies, then it's cold gas, the molecular gas and the atomic gas that it has, which eventually turn into stars. New stars are formed from molecular clouds, and it's aided by the presence of cold gas that can be stripped off as the galaxy moves in. Whereas if it's not in a dense region, there's nothing to strip it off. And once the fuel of star formation is stripped off the galaxy, then it means that its star formation rate is going to drop, and that's one of the reasons that's happening. The other thing is called, we use anthropomorphic terms for galaxies. It's called harassment, and harassment is that when two galaxies are interacting with each other, due to the interaction, a lot of the gas can be stripped off the galaxy, and these are galaxy-galaxy interactions, collisions, or very near collisions in which you can strip off the gas, and that can cause the falling of the fuel. And then there is the effect of strangulation, which means it's also another human term, is that when a galaxy is which has a store of cold gas around it, it enters a cluster, then the galaxy themselves loses the store of cold gas around it by it being heated. And so if this galaxy's store of cold gas gets heated, hot gas cannot turn into stars. And so the fuel is not lost, but its fuel goes into a form in which it cannot really aid star formation. So these are the various things that can happen. So you can see examples of this. For example, we can see galaxies that are moving in a cluster in which the gas, here's the radio observation of the cold gas of the galaxy that's losing its gas. And you can do simulations in which you can see this. You can see the effect of strangulation in simulations and harassment as two galaxies merge, how the gas is lost. And you can see the effect of strangulation. I'm going to stop here and essentially summarize by saying that galaxies are the basic building blocks of the universe. They are found in all kinds of different environments, in clusters, in little groups, mostly, rarely singly. And then when they form with a lot of these components. It has the stars, it has the dark matter, it has the gas and dust. And the gas, the cold gas and the molecular gas, which are really now detectable through radio astronomy. Because this is a radio astronomy school, I have to highlight this, that radio astronomy helps us find the fuel of the gas that and the gas that forms the stars, and the forming stars and the quenching of star formation are the major evolutionary stories of galaxies. And these are, to study galaxies, radio astronomy plays a very important role, because you can study these. The other thing radio astronomy gives, which you've already encountered, is studying the effects of the supermassive black hole in the middle of the galaxy. And and it's mostly found in continuum observations, the effect it has on the surrounding medium within the galaxy itself, when the galaxy becomes active and the nucleus becomes active. I'll stop there and see if there are any questions.
Hello, sir. Thanks for the wonderful talk. I had a small doubt. There was somewhere you addressed that spiral galaxy is better in the rate of star formation than an elliptical one. Can you please elaborate on why is it so? Like due to the structure or angular momentum stuff or something like that?
No, so I was going to say that this, this is an observational fact that spiral galaxies have more star formation on a whole than elliptical galaxies. Now, this is the thing that I was trying to say right at the end as to why this is, and this is because to have star formation, you need molecular gas. I didn't establish this, but take this as a fact. That's a separate lecture. Why hot gas cannot turn into stars? Because there's something called the Jeans mass that you can calculate, which is the typical size of things that will collapse to form. And star-like things are formed, it turns out, from the kind of abundances and pressures and temperatures that you find in molecular clouds, where the predominant component are molecules. And along with it is, of course, the atomic component. It's mostly hydrogen, atomic hydrogen, along with the various molecules, simple molecules that are formed. Now, molecules and atoms can exist in a plasma only in the cold form. You can't find it, for example, in million degree gas. You can find it in gas that is 10 to the 2 degrees or 10 degrees, things like that. And so these are the cold parts. These molecular clouds have certain conditions for star formation. Now, they are found mostly lined up in the disk of spiral galaxies. And particularly the perturbations that cause the star formation, cause these things to collapse, are very conducive along the spiral arms of the spiral galaxies, right? In elliptical galaxies, we don't find, first of all, the molecular gas and the atomic gas to this extent. And we also don't find the kind of local conditions that will help these things to collapse to form stars. And we're trying to figure out why this is. And it turns out that elliptical galaxies are mostly found in very dense environments like clusters, in which by the time they've turned elliptical, due to galaxy-galaxy interactions that led them to become elliptical, or the effect of the environment, which has stripped off the gas as the galaxies move in the cluster, the raw fuel which will turn into the gas, into the stars, the atomic and molecular gas, has been stripped off the galaxies. So elliptical galaxies not only don't have any star formation, they don't have any gas either. Very, very little gas. And you don't see any dust in them, which is kind of a byproduct of star formation, which shows that you're not missing hidden star formation. Actually, those things are not there. And in the elliptical galaxies, you also see an abundance of very hot gas, which you can find in X-rays. And so the other thing I did not talk about is that at the center of elliptical galaxies, the supermassive black hole that sits in the elliptical galaxies, which are much more massive there, plays an important role in heating up the interstellar medium. Whatever gas remains in the galaxies are found in the hot state, not in the cold state. And so hot gas doesn't collapse to form stars. So there are many reasons why elliptical galaxies don't have stars, star formation, new star formation. It has a lot of stars, but that's because those stars have formed in the earlier disk galaxies that merged to form this current elliptical galaxy. All of them are very old. They're not new star formation. I hope that answers your question.
Yes, it does. And another query, sir, like for the spiral galaxies, why is a particular spiral, I mean, why is a particular plane favored over the other planes for the spiral formation?
Um, well, I mean, if, for example, you have a spherical system that collapses, it will collapse. It never collapses uniformly along all three directions. There will be some kind of a perturbation that causes it to collapse, and that will have some kind of a preferred direction to begin with. But imagine all clouds that are collapsing will have some angular momentum because there's something Fred Hoyle pointed out in the 1950s. If you have two clouds sitting there, even if they're spherical, they will have tidal interactions on each other. And so the farthest parts of the clouds will attract each other in a different way than the nearer parts of the clouds, right? And so as a result, they will get torqued. And so these tidal torques will cause them to rotate. And so if you think of the initial universe as matter formed, they have these clouds all over the place, and they will gain angular momentum by tidal interactions. Now, once you have an angular momentum, you can't lose it. So now it collapses. Once something collapses, which direction would it prefer to collapse? It will prefer to collapse perpendicular to the rotation, because the rotation itself, the centrifugal force will support rotation, will collapse along that plane in which it is rotating. So it will preferentially collapse perpendicular. And this is why you actually see a lot of these disk galaxies rotating along perpendicular to a certain axis. And this is a very kind of simplistic argument. There are a lot of other effects that go on, but I think this is, in simulations, you can see this happen.
Hello, sir. I have a question. So, for the spiral galaxies, you said the spiral arms are basically the local increase of density due to some perturbations. So, why is these regular spirals are formed, like not some random structures or so, for the perturbations? Why they are so regular?
A very good question. I mean, I did not answer this because it's not possible in 50 minutes to do this. This is a whole course on its own. And if you want to do astronomy, you can do this. Why these are spirals and these density waves have spiral structures was a very interesting subject that was developed in the 1960s, 1970s by Shu and Lyndon Bell and people like that. You can see that if you stir your teacup, you will find that on the surface you see spiral-like waves. So spiral density waves are very naturally come from differentially rotating disks. If you have an azimuthal symmetry, cylindrical symmetry, and you can work out that the whole thing is not turning as a solid body, and it's turning with a certain angular momentum, which is different radius. At different radius, the rotational speed is different. You will find that the most predominant perturbation that comes is spiral. And I can only say that in a qualitative fashion, but this can be worked out mathematically. Very interesting, very hard theory, but very interesting theory has been worked out And please go ahead and read some books on this. I mean, there are very nice books on galaxies in which there are whole chapters dedicated to how spiral structures form. These are resonances in the small perturbations which cause resonances which take the form of the spiral patterns. And it's also interesting to see how many spirals, for example, will form in a particular galaxy given the kinds of symmetries it has. Some have 2 spirals, some have 3, some have 4, etc., etc.
So I had a question regarding the galactic rotation curves. So can I ask? Sorry, Zamir sir, are you talking?
Yeah, please go ahead. Pranav, you go
Yeah.
ahead.
So yeah. So the flattening of the galactic rotation curve today we accounted for the dark matter or the extra gravity which is there. But I came across this theory called MOND, the modified Newtonian dynamics, which I'm not too familiar with, but tells that the relative acceleration of the stars is accounting for the extra gravity. So I wanted to ask whether there are any observational evidences which support this new theory.
Not a new theory. It's dead in the water. I mean, it came in the 70s, 80s when I was a student in the 80s. People were talking about it a lot because Wittgenstein, who's a very famous astronomer, worked with Hawking, as you know, proposed this theory, but it lasted about 10 years. You still read about it in books, but nobody believes it anymore for the following reason. I didn't talk about dark matter today because I thought somebody else probably has. And you have these rotation curves which are flattened out to a large distance, which show that even outside the stellar limits of galaxies, there is quite a lot of matter because otherwise the rotation curves would fall in a Keplerian fashion. Now, then of course people said, but we don't see this dark matter. So what is this dark matter? Maybe we can modify Newton's laws on galactic scales. So very large scales and kiloparsec scales, Newton's laws actually have some other term. It's kind of an exponential term, which vanishes at very small scales, but is very important to it. So that's the modification of Newtonian dynamics. And so the Newtonian potential, which is, as you know, Gm over R, that is the potential, was modified with another term. And it was tuned. Now, the problem is in any such new theory, if you have introduced extra parameters, it fits certain things because the parameters you can adjust so that it fits a certain observation. But it has to fit all the other observations as well, right? So, and gravitation has many other implications, not just rotation curves. So, for example, when gravitational lensing was discovered, and you found how much light bends around a massive object like a galaxy, and you can exactly find how much matter there is from that galaxy. And you did it, you take the same galaxy with its rotation curve from its mass, you take the gravitational wave and do the same thing, you find the same mass. And MOND works in gravitational lensing in a different way than in the rotation of the spire. So MOND died as soon as gravitational lensing started producing mass maps, right? And then there are many other ways now of measuring mass. You can measure the mass of a galaxy or a cluster through X-rays. MOND doesn't work there either. So it's a very interesting subject, and such interesting things come and go, and this lasted about 10 years.
Okay, thank you.
Sir, I had a question.
Yeah.
So from this graph on the screen, we see that the galaxies in our local universe have lower star forming rates, and galaxies further away at higher redshifts have higher star formation rates. So can we conclude from this graph that the overall general trend in time is that star formation slows down in galaxies? Or is it just that the galaxies which have higher star formation rate happen to be further away and further back in time?
No, this is now, I mean, I'm showing you a little older plot. This is now based on many surveys that have been done with galaxies in different parts of the sky using different ways. Now, here you're seeing that the star formation, which I didn't explain, the star formation is measured in this particular plot from 4 different measures. This is, for example, the UV, which ultraviolet observation, the ultraviolet observation of a star, of a galaxy tells you how many new stars there are, because the hot stars emit in the ultraviolet, right? So it tells you how many hot new stars there are. The H alpha gives you another indication of star formation, because the certain H alpha line is seen in newborn stars. The infrared observations at about 100 microns or so tells you about the dust that accompanies star formation, and it glows around. The emission from this dust is at about 100 microns. And the radio also gives you an indication of the star formation, radio continuum observations, because again, newborn stars are often extremely large, and they have very short lifetimes, and they go supernova, and the supernova remnants emit radio. So quite different measurements, and they all give you roughly the same results. And now this has been done from various surveys from different parts of the sky. And this is now a general trend. What the plot that you see there is an average of all galaxies found at that redshift. And now we this graph can go up to 5, 6 redshift easily, because many galaxies found there. So this essentially shows the trend of all galaxies at a certain redshift behaving in a certain way. The mean star formation at a redshift of 2 is given here. The mean redshift doesn't matter where they are, which environment they are, whether in a cluster or not, which direction of the sky. This is the mean redshift. So you're looking at shells around you in distance or in redshift, and you're looking at the mean in that distance or redshift, right? So this is a general trend. I think that's what your question was, right? So it
Yeah,
doesn't.
so can we conclude? So from this, do we conclude that older galaxies have a higher star formation rate because the galaxies at 1 to 2 redshift further away?
You have to worry. Just I'm interrupting you, because think about what the word older means, right? Imagine you're looking far away. You're seeing a galaxy as it was when the universe was younger, right?
Right.
When you say older, you mean you take a galaxy now and you measure its age. And so that has to be at a redshift of 0. When you're looking at something at a redshift of 1, it means, because the light takes such a long time to come to you. So you're looking at a galaxy as it was when the universe was half its age. So you're looking at a younger universe. You have no idea what that galaxy looks like now. It might not even exist. You will know another, 5, 10 million years later, what that galaxy looks like now. So when you say older galaxy, you actually mean galaxies when the universe was younger.
Yes, sir. Yeah.
And you're looking at it as it was at that time. And this graph means that. The graph means that if you are looking at the universe when it was, so for example, a redshift of 1 means the universe is z plus 1. That's how it goes. So the universe is half its age at that time. And there, if you look at galaxies when the universe was half its age, the average star formation is this. When the universe is now, this is redshift to 0, is now, the star formation rate is much lower.
10 times lower.
Right? And this is the average of all galaxies I know. And you can look at something that's 1.5, so the universe is 2.5 times younger. Then you look at the average age of all, average star formation rate at that time. So you have to worry about when you use the word older, if an old person now, I'm not talking of the old person as it's old now, but I'm talking of when this person was half their age.
Yes, sir. Okay, thank you.
Sir,
Yes.
I have a doubt. Yeah. So in this figure, like there are lots of error bars. I mean, the error bar along the z-axis is understood, like how can they be measured, but along the log axis, like how are the error bars measured?
Yeah, so that's a very interesting question. Error bars can exist in both axes. The error bar on the z-axis actually, in most cases, is smaller because you can measure the redshift very very accurately, but there are certain galaxies for which the actual redshift cannot be measured because the spectral lines are missing. And so there's an estimate made from their photometry and things like that. So that's the error bar is large. The y-axis error bar is actually pretty large, and that is because you can never detect star formation directly. You have to take a proxy of star formation and try to estimate the star formation. You're not waiting, for example, for 1,000,000 years and seeing how many stars formed. What you're doing is you're looking at, for example, as I pointed out, those different indexes. You're looking at the ultraviolet light from a star, from a galaxy. Now, you're assuming that the ultraviolet light comes from the most massive stars, because ultraviolet stars are 20,000, 30,000 degrees hot. These things don't last very long, so they are indicative of young stars. And from that, you build a model saying that if, for example, there's so much ultraviolet emission from this galaxy, then there are so many young stars. And so many stars are forming every year, right? So there's a model involved. And that model has certain parameters that you have to calibrate. And as a result, you get the error bar, right? Similarly, when you have gas or dust, you have models of how much dust a star formation produces. And so by measuring the amount of dust from its infrared emission, you then, by a physical model, have to estimate how much star formation that corresponds to. And there is an error in that translation. So this is what the error bars reflects. As we understand more and more of the physics, the complicated physics that goes into these modeling, and also the measurements themselves have errors because you have to correct for all kinds of things. You have to correct for absorption within the galaxy, correct for absorption within our galaxy, and how much light has been lost while before you measured it. That kind of stuff you have to make. As our measurements get better, as our models get better, those error bars are going to shrink.
Okay, sir. Thank you, sir.
Yes, so this is much of a distance scale then, right? That further the distance is more is the redshift.
Yeah.
So isn't there a possibility surrounding has a lower star formation rate from starting itself?
Yeah, so very, very far away galaxies, when we don't know when galaxies started forming in the universe, maybe at a redshift of the farthest galaxies that we found in the universe are at a redshift of maybe 8, 9, 10, something like that. And but their star formation rate is very small. And when the first galaxies formed, they're very small galaxies. And as the universe became older and older and older to about a redshift of 2 or so, the star formation rate rose. That is also a very interesting subject of research right now. Why did it rise? We're talking about why did it fall from 2 to now, redshift of 2 to now. But as the galaxy built itself together and the components got together, we have to find out why it inspired more and more star formation. And it's probably due to some of these effects, which are to do with the fact that as galaxies grew bigger, in getting more and more gas in them, the fuel of star formation started building up in the galaxies. And this is the growing phase of galaxies, and comes to a maximum. And then many of these galaxies get into clusters where this gas is stripped off them again. And then they start losing the fuel that will form into stars. So this is the building phase, and this is the depleting phase. But we don't have a very good understanding of the building phase yet, because very far away galaxies are more difficult to study. And we are getting bigger and bigger telescopes to study more and more galaxies at redshift of 4, 5, 6. And the assembly of galaxies, how the black hole comes into place, how the dust and the gas components come into place, are really wonderful subjects of study right now. If you want to do a PhD thesis in this area, this is the time to do it.
Okay. So I wanted to ask that the galaxies which you observed at zero redshift are the galaxies nearby us, right? And
Yeah.
yes, so isn't there a possibility that those galaxies have low star formation rate from starting itself?
No, this is an average over thousands and hundreds of thousands of galaxies, and so you're talking of. So then you're saying that the galaxies that are nearby maybe didn't have star formation at all, right?
Yeah,
Uh,
from starting.
then they won't have galaxies, right? So in galaxies, you see 10 to the 11 stars, 10 to the 12 stars. They would have had to form sometime. All I'm saying is the current rate of star formation, new stars being born, is low. But you see 10 to the 11 stars in the galaxy, 10 to the 10 stars in the galaxy. So they were formed at some point. If there was no star formation in the galaxy in their entire life, then there will be no galaxy.
Okay. So, but in a long time, like the star can form at slower rate also.
Yeah. So as I said, the current, I'm talking of our own galaxy, which has 10 to the 12 stars, has a rate of 1 star per year. That's the star formation rate, and I'm calling it very, very low because it's the age of our galaxy is probably 10 to the 10 years. So, and in that, if it had the current star formation rate, 1 star per year, then it would be 100 times smaller. So, sometime in the past, it had a much higher star formation rate, maybe around this time. You can see this is a log scale, so this is 100 times more star formation rate, and then it came down. So you can look at the current star content of the galaxy and say, at the star formation rate now, will it have reached this mature age? And the answer is no. It had to have a higher star formation rate in the past. And it turns out you could have 2 scenarios. One is that right from the beginning to now, star formation goes on increasing, and then decreasing at different rates. But the interesting thing is we see in the universe that if you take an average over thousands, 10,000s, 100,000s of galaxies, at a redshift of 2, it seems to peak. And at a redshift of 5, it's fallen there. So it's all happening together as the universe ages. It is not out of step. And each galaxy itself has a history of star formation that goes up and then comes down. But the thing we would like to understand is why it all happened when the universe was 3 times smaller or younger. And why it is coming down now to a level that almost no galaxy is forming any stars, right?
So this is based on the assumption that the galaxies were born in a finite time, right? And born before some finite time.
Yeah.
Okay.
Of course, I mean, when the universe was formed, there was no galaxy, there was no star, there was nothing. There was only energy. So galaxies would have to form at some point, and we think the epoch of galaxy formation, we haven't found that yet, but it's roughly around 10 or so, 8 to 10. That's a subject of its own. But if you go much further than that, you won't have galaxies.
Okay.
Sir,
Yes.
sir, I just want to ask a question regarding the upcoming new telescope by NASA, the James Webb Space Telescope. So they are claiming that it can extend the discoveries of the Hubble Space Telescope with much longer wavelength coverage and increased sensitivity. And with these features, they are saying that they can look back into the very beginning of the time and can observe the formation of the very first galaxies, etc. So, do you think that's possible? Like their expectations can, it's practically.
Well, when you have a bigger telescope, you see much further because you gather more light and you see much fainter things, and fainter things often tend to be much further. So the James Webb Telescope will be certainly a much more important telescope in terms of in space. First of all, in space, the resolution is much better because we don't deal with atmospheric blurring. And the Hubble Space Telescope in space is only a 2.5-meter telescope, which is a very small telescope. I have a 200-meter telescope that my institute owns, which is 100 kilometers away. And there are, 5 telescopes I can think of in India that are that big. The reason Hubble Space Telescope is very special is that it is in space, and so it doesn't have to deal with the blurring of the atmosphere. It has wonderful resolution. It's got very nice cameras, etc. The James Webb Telescope will be much bigger. It's a 6-meter plus telescope, and so it will be much bigger, and it's going to concentrate mostly on infrared observations. So there it is interesting because it will look at very far away objects. Why? Because most of the optical light, as it is very far away, if it's very far away, it means that it's also moving away from us. Hubble's law says that redshift is high means things are very far away. So what the Hubble Space Telescope is studying, which is the ultraviolet part, which is the newborn stars, if it's redshifted, it will move into the infrared. The telescope is finding near us, you will see at high redshift because you're looking at the infrared. So not only is it a big telescope that can see faint objects and so further away, it will also normal optical light or UV light will be redshifted for higher redshift objects, right? And redshift means that its wavelength moves. So something, if I take a picture of a galaxy with a Hubble space telescope now with a blue filter, now that gives me an idea of the near young star formation. Say at 400 nanometers or 300 nanometers, at a redshift that is 2 or 3 times more than that, that thing is going to move into 1 micron. And it will move into 2, 4 microns at further and further distances. This is exactly what the James Webb Telescope will see. So this is why we believe that it's going to give us a very different view of the faraway universe. And we are really looking at to find the epoch of galaxy formation, when the galaxies form, and even beyond. So that's I think, so that's why we are hopeful about the James Webb.
Okay, sir. Thank you.
So Ritvik is asking, is Newtonian mechanics is enough to calculate time period of satellite galaxies, or some other mechanics is used? And his second question is, how was Saraswati supercluster discovered, and what method was used?
Okay, the first question is yes, because Newtonian mechanics is adequate if the velocities that are involved are not very close to the speed of light. And these galaxies are moving with respect to the universe at about 30, 40, 100, 200 kilometers per second, whereas the speed of light is few lakh kilometers per second, 3 lakh kilometers per second. So this is much lower. So there is no relativistic correction needed. And the other place where Newtonian mechanics fails is if the densities are very high, like neutron stars or black holes. And these galaxies don't have these densities. Galaxies are essentially very empty objects. So yeah, in Newton mechanics is absolutely all right. And the attempts that have been made, many attempts have been made to modify. So MOND, there has not been, I talked about MOND, but there has not been one MOND. There have been many MONDs tried where Newtonian mechanics has been tinkered with, small scales, large scales, etc. But we have found no evidence that Newtonian mechanics needs to be changed. Now, I did not talk about superclusters here at all. I knew that there was talk on clusters yesterday by Rita, but that's a different topic on its own. But clusters, superclusters are discovered by looking at the cosmic web and looking at large concentration of galaxies in sky surveys. There have been many superclusters discovered in sky surveys. I discovered something called the Shapley supercluster in the 1980s, which was got 40 clusters over about 50 megaparsecs or so. Since then, many others have been discovered, the Sloan Great Wall, etc. And the Saraswati supercluster, which we discovered here, started with an observation of 3 clusters merging together in a system which Jaideep Bagchi and I first started looking at long time ago, about 20 years ago, when he studied it with optical telescopes and X-ray telescopes, and then realized that it's part of a much larger structure. and it became the topic of thesis of Shishir Sankhayan, who did a wonderful analysis of lots of galaxies in sky surveys to find that it was a system of much more than those 3 clusters we found that are merging together. And we believe such big structures exist. I mean, it's just difficult to find. The Shapley and others were much nearby. This is a much further away system of clusters. And I think as we look at these bigger sky surveys at higher distances, there aren't too many sky surveys. The Sloan survey, etc., are all very nearby. Higher distances, we find many of these very interesting structures. That's all I'd say now.